For the model with packs in male, it's smaller, 1330. So using this criteria, the AIC would suggest that the second model is the better model to use. As a general rule, if you're comparing two different models to be your candidate for the final model, there's more statistical justification for comparing the AICs rather than the -2 log L. So statistical theory suggests that the AIC should be chosen. And if that was the case, you'd make your final conclusions on the second of the two models I just talked about. Well, in this case, the AICs are very similar. The -2 log Ls are very similar. You're not going to get a different conclusion probably from either of these two models. And you didn't. The odds ratio for male was 1.97, 1.98. It was around 2 in both of those situations. But in other situations, I would suggest using the AIC statistic to decide which of your two models is your best model. We'll talk about this again when we talk about linear regression. Looking at the AICs, it's sort of like looking at an adjusted R-squared. We'll talk about that when we get to linear regression later today, if not next week. But let me ask you one other question as a group. We had two models. They modeled, I should say, the relationship between smoking and your risk of developing heart disease in two different ways. So what sort of assumptions are being made in these two models? What are they talking about? Assumptions are they making in terms of the effect of smoking? What are they talking in models in terms of the effect of male versus female? So I think an important aspect of model building is to appreciate what assumptions are being made when you fit a model to a given data set. So let's use the two models again that we were talking about. Model number 1 has male and smoking represented as a categorical variable with 3 indicator variables for the 4 categories. And model number 2 has male and smoking, but now smoking represented as a continuous variable. What assumptions are being made in model 2 that are not being made in model 1? The question is, what assumptions are being made? In terms of smoking, the first model, where you had PAX1, PAX2, and PAX3, is assuming a conditional step function to describe the relationship between smoking and your risk of getting disease. The second model that had PAX in it for smoking is assuming a linear relationship. And both models are assuming what we call additivity, meaning that the effect of smoking doesn't depend on whether you're male or female. Smokers have the same effect regardless of your sex. And likewise, both models are assuming that sex has the same effect. The effect of male versus being a female is the same regardless whether you're a non-smoker, a 1-pack-a-day smoker, a 2-pack-a-day smoker, or a 3-pack-a-day smoker. To see that pictorially, this is sort of what's being implied by the first model. The model says your log odds of disease is B0 plus B1 times male plus B2 times PAX1 plus B3 times PAX3 plus B4 times PAX4. Here's a model that has cigarettes as the x-axis. I didn't label the y-axis. I should have. What we have here is the person's log odds of developing coronary heart disease. What's on the left-hand side of the equation. Now, if you're a non-smoking female, your value for male is 0 because you're a female. Your value for PAX1 and PAX2 and PAX3 are all 0 because you're a non-smoker. So a non-smoking female gets a value for her log odds of disease, which is just B0. If you're a non-smoking male, your value for male is 1. Your value for PAX1, PAX2, and PAX3 are all 0 because you're non-smoking. So 0 plus B1. So really what I don't have on this curve, on this pic, is I should have 2 points right above the zeros. This is where this intercept of this point where the x-axis meets the y-axis, the horizontal and the vertical, corresponds to the non-smokers. I should have 2 points there, a B0 for a female, a B0 plus a B1 for a male. But if you are a smoker, and you smoke anywhere from 1 cigarette a day, or 10 cigarettes a day, or 19 cigarettes a day, or 20 cigarettes a day, you have the same, the model says your risk is the same. Because if you're a 1 cigarette a day smoker, your value for male is 1, your value for PAX1 is 1 because you do smoke part of a pack a day. Your value for PAX2 is 0, your value for PAX3 is 0. So your risk, your log odds of getting disease is B0 plus B1 plus B2. If you're a 2-cigarette-a-day person or a 9-cigarette-a-day person, as long as you're smoking a pack a day or part of a pack, all those people are treated the same. The model assumes that if you're a male, hovers around a particular value. That value doesn't change as long as you don't smoke more than 20 cigarettes a day. If you are a 1-pack-a-day female, that is true for you also, but you don't have a value for your value for male is 0. You don't get the B1 term. So the dotted line represents what the assumed common log odds of disease. Regardless whether she's smoking 1 cigarette, 10 cigarettes, or 19 cigarettes. But if you smoke 2 packs a day, the risk changes because now you're no longer packs 1, you're now packs 2 is equal to 1. Packs 1 and packs 3 are both equal to 0. So now a male and a female has a different level for their risk of disease, a different level for their log, a different level for their log odds. And likewise, if you're a 3-pack-a-day smoker. So what this model assumes is that there's a conditional step function relationship, that your log odds of disease increases with the amount of smoking you do, but it increases with steps. You're at one level if you're a non-smoker, you're at another level if you're a 1-pack-a-day smoker, regardless whether you're 1 cigarette or 19 cigarettes. You're at a different level if you're a 2-pack-a-day smoker, regardless whether you're a 21 cigarette-a-day smoker or 39 cigarette-a-day smoker. You're at a different level if you're a 3-pack-a-day smoker. So what this model assumes is your risk could go up with more smoking, but it only goes up when you smoke an additional part of a pack of cigarettes. That's the assumption that's being made here, because that's what you assume when you put people into risk categories by levels of smoking. When you decide to put everybody in the same category of a 1-pack-a-day smoker, regardless whether they're smoking 1 cigarette a day or 20 cigarettes a day, you're calling them a 1-pack-a-day smoker. And you're saying your risk doesn't change as long as you're smoking part of a pack of cigarettes. It doesn't matter how much of that pack you're doing. But it does change when you move to 2-pack-a-days. It does change when you move from 3-pack-a-day. So a step function assumes that your risk is common within the category, but can change when you move outside of that category. That's where the steps happen. So this is the assumption that was being made in this first model. And notice the assumption is that the difference between males and females, the gap between these two lines, is the same regardless whether you're a 1-pack-a-day smoker, 2-pack-a-day smoker, or a 3-pack-a-day smoker. The model is assuming that the height of the step for male versus a female at a given level of smoking does not depend on the level of smoking. That's what we mean by additivity. The effective male sex does not change regardless of your level of smoking, always represented by this number B1. Likewise, the effective being a 2-pack-a-day smoker rather than a 1-pack-a-day smoker, the change in these steps for males is the same as the steps for females. That's what we mean by additivity. But in the second model, we made a different type of assumption. If we talk about females, if we set male equal to 0, what we have is this model says a woman's log odds of disease is B0 plus B2 times her level of smoking packs, 0, 1, 2, and 3. But that's the equation of a straight line. This model is assuming females have a linear relationship in terms of their level of packs on their log odds of getting disease. There's a straight line with an intercept of B0 and a slope of B2. Males, on the other hand, have a value of 1 for male. This model says a male smoker's log odds of disease is B0 plus B1. But again, B2 times pack, another straight line with the same slope, and now the intercept is B0 plus B1. So this model is making a different assumption. It assumes that your conditional log odds of disease increases with the amount of smoking. It increases the same amount as you move from a non-smoker to a 1-pack-a-day smoker, or a 1-pack-a-day smoker to a 2-pack-a-day smoker, or 2 to 3. It assumes that every additional pack of cigarettes you smoke increases your log odds of getting disease by a value of B2. That's the slope. It's telling you how much your Y value changes when you increase your X value by 1 unit. That's what a slope represents. It's assuming that same slope holds for both males and females. So here we're making an assumption of linearity to describe the relationship between the continuous variable packs